Now that our well has been successfully drilled, our next decision is whether to complete or abandon it. The video library includes an entire series on open hole logging and well testing, common methods of evaluating a well. We won't spend any more time here on the evaluation techniques used to determine a well's potential. Instead, we shall continue to follow the activity at the drill site.
Well, it looks like we made a good well. Our next step will be to run the final string of casing, the production string. I'll see you on the rig floor.
Our well will be completed as a cased and perforated completion. That is, the production casing will be run through the productive interval and cemented in place. Then, after the cement is set, we'll selectively perforate the casing with the shaped jet charges in order to allow the formation fluids to flow into the well bore. Some alternative basic completion methods include the liner completion and the open hole completion. In a liner completion, the production casing is set above the producing zone. The bottom of the hole is drilled, and another length of small diameter casing hung from near the bottom of the production string down inside the well bore. This liner may be slotted and not cemented, or it may be regular casing which is cemented and then perforated. An open hole completion is similar, except that no liner is run. That is, the productive zone is not protected or inhibited by any casing. It is simply an open hole.
After our contract casing crew runs the final casing string, cementing follows the usual procedure, although stage cementing may be necessary in particularly deep wells. In those situations, cement is pumped around the casing shoe and partway up the annulus, and then ports in the casing are opened and cement is forced into the upper portion of the annular space. After the cement has set, any cement remaining inside the casing must be drilled out and the casing flushed clean of debris. It is important that the inside of the production casing is clean. It is also important that the cement form a competent seal between the casing and the borehole over the entire open hole interval. To be sure that this is the case, and to prevent communication between the formation behind the casing, an acoustic cement bond log can be run inside the casing on electric line to give an indication of the quality of the cement job. If the cement job or the cement bond is poor, we may have to perforate the casing and squeeze cement behind it into the void space, what we call a squeeze job. At this point, some operators might move the rig off location and bring in a smaller, less expensive rig to finish the completion. The choice depends on the complexity of the completion, the depth of the hole, the pressures that have been encountered, and perhaps even whether or not time is needed to install a sales pipeline for the production. We also run a correlation log inside the casing. This log has a gamma ray track which we can correlate with the earlier logs run in the open hole evaluation. It also gives an indication of each casing joint coupling, collars as they're called, that it passes. We use the correlation log to tell us where to perforate or set down hole equipment by relating the open hole logs and the correlation log through their gamma ray curves, and then using the casing collars as a guide to depths. Whichever completion rig is used, the tubing must be measured into the hole and the drilling fluid circulated out. Perforating should be done with a clean, solids-free fluid in the hole if possible. If perforating is done at this time, the tubing is removed and the perforating gun is lowered and positioned according to the casing collars on the correlation log. The gun is fired and retrieved. If through tubing perforating is part of the completion plan, the perforating gun is lowered through the tubing or on the end of the tubing and fired after the well's surface flow control equipment is connected to allow the formation fluid to rush into the well and clean out the perforations. With the well perforated, it may now be time to stimulate the well by pumping acid into the formation to correct damage caused by mud or mud filtrate, particularly in sandstone reservoirs, or to actually enlarge the flow passages in limestone reservoirs. Or we might pump a viscous fluid with sand in it down into the well to hydraulically fracture the formation, increasing its ability to flow hydrocarbons. We don't need to do that on this particular well. At least we don't need to during our completion operations. If the well doesn't produce as much as we expect it to, stimulation might be considered later. In some areas at this point, we might also need to pack the inside of the perforated interval with clean sand. We're calling this a gravel pack. This is done to prevent formation sand from flowing into the well. Next, we'll run our tubing string and packer into the hole for the final time. The tubing must be spaced out so that it fits into the packer set at the bottom of the hole and yet also hangs from the tubing head connected to the casing at the surface. With the tubing landed, the BOP stack can be removed and the Christmas tree installed. Finally, the rig will be released and the location prepared for any surface production facilities that may be needed. You should realize that every completion is unique. The actual procedures used in any given situation will vary depending on the type of equipment being used and the complexity of the individual completion. But one thing that never changes is the paperwork.
That's the typical completion procedure: running the final string of casing, perforating, running tubing, and setting the tree. Let's take a moment to look a little more closely at a few of the more complex completion procedures mentioned earlier, specifically perforation, stimulation, and sand control.
The use of steel casing to line the well bore and isolate producing zones is only practical when a method for easily reopening those zones for production exists. In jet perforating, a shaped charge of explosives is used to produce a high-pressure stream of particles, which displace the metal, cement, and rock to form a perforation. A variety of gun designs exists, depending on whether the gun is run into the hole on an electric conductor line or on the end of the tubing, whether the gun is to be fired through the casing or through the tubing, whether the gun is retrievable or expendable, and the size of perforations desired. Perforating can be carried out in several different ways. Conventional overbalanced perforating done through casing with an electrical conductor line and a heavy fluid in the hole, which creates hydrostatic pressure greater than the formation pressure. Conventional underbalanced perforating, usually done through tubing with an underbalanced well bore, that is, a small head of fluid in the tubing to allow immediate flow when the perforations are created. And tubing conveyed perforating, in which the gun is run on the bottom of an empty tubing string, allowing the maximum amount of underbalance during perforating. Underbalanced perforating is a technique which relies on the sudden force of the flowing hydrocarbons to flush debris from the perforations and ensure that none remain plugged, causing lower productivity. One of the advantages of the cased and perforated completion is the ability to selectively stimulate specific formations when they're isolated from one another by the casing. Well stimulation includes two common techniques: acidizing and hydraulic fracturing. Acidizing involves the pumping of an acid solution, usually hydrochloric and hydrofluoric acid, down the well and into the pore spaces of the rock formation. The acid partially dissolves the materials found in between the grains of the rock, or dissolves a portion of the rock itself, increasing the size of the flow passages. A variety of other chemicals is added to the acid solution to ensure that it does not harm the steel tubing and casing and to maximize its effect on the formation. If the acid is pumped at a pressure great enough to fracture or split open the rock, it becomes an acid fracture treatment. Fracturing in general is another form of stimulation used to create flow passages in a rock where none or few exist. In hydraulic fracturing, a fluid is pumped down the well bore at pressure sufficient to cause the rock to split apart, usually vertically, allowing the fracturing fluid to enter. As the fracturing fluid is pumped into the fracture, extending it further from the well bore, a proppant material, usually sand, is carried along in the viscous fluid. When the pumping stops, the frac fluid flows back into the well bore, leaving the proppant to prop open the crack and prevent it from closing up completely. In this manner, a high permeability pipeline to the wellbore can be created, often extending thousands of feet out into the reservoir on either side of the well. Typically, a large amount of specialized equipment is required for a fracture treatment, particularly a massive one. The fluid and proppant must be steadily blended and sent to the rows of pump trucks which work together to pump the mixture into the well at a steady high rate and pressure. In some places, such as the U.S. Gulf Coast, stimulation is not needed to induce production. In fact, the formations are already so unconsolidated that they themselves actually flow into the wellbore, creating an entirely different completion requirement, sand control. Methods for controlling sand production have generally involved one of two approaches: a metal or sand grain barrier which screens out the formation sand but does not inhibit fluid flow into the wellbore, or an epoxy resin which is injected into the rock and hardens to form a consolidating binder for the formation sand grains. Metal screens or gravel packs work in a manner analogous to a large crowd of people trying to leave a theater through a small door. Each could pass through individually, but when several try at once, they form a bridge, preventing those at the rear from moving at all. In sand control, bridging methods employ wire-wrapped screens with openings carefully sized to allow the formation sand or gravel pack sand to be deposited against them. Gravel packs are designed based on the analysis of the formation sand grain size distribution, so that the screen and gravel pack sand will prevent formation sand movement, but not inhibit formation fluid flow. Sand consolidation techniques are best applied to shorter completion intervals, where precise placement of the epoxy resin is possible. The plastic-like material is generally displaced into the formation and allowed to harden, binding the formation sand grains together. If the plastic is pumped too far into the reservoir, or if it isn't distributed over the entire interval, sand production will continue. On the other hand, if the plastic is under-displaced and left to harden inside the tubing, the well may not produce at all.
Now you've seen our well completed and learned a little about several of the different completion procedures used. Remember, every drilling and completion program is unique, and although the sequence of events we have followed is typical, it is by no means the last word on the subject. Section 3 in your manual gives you an idea of the variety of drilling and completion practices in use worldwide. Please take a look at them after reviewing what we have just covered. Then work exercises 6 and 7 in your manual. This module has covered quite a bit of material. You should now feel comfortable with the concepts and terminology related to drilling and completion practices. Of course, drilling and completing our well is only the beginning. Production and reservoir management are an important part of the oil business and are covered in the next module in this series. I'll see you there.